Hello everyone, I am Sudeep Datto. I am a PhD student in the Department of Computer Science from Missouri University of Science and Technology. Today I am going to present my most recent work which was published in IEEE Transactions on Network Science and Engineering in 2021, and the title of my paper is Prioritized Content Determination and Dissemination Using Reinforcement Learning in TTNs. Before explaining the title, let's first see what scenario we are considering. So we are considering a battlefield or disaster affected scenario. For example, in a battlefield, different groups of soldiers are deployed by the command and control center, and those groups of soldiers have different mission goals. That means they have different interest on the surrounding. So these soldier groups need to uh, collect information from the surrounding, and they need to send the information to the command and control center for situational awareness. However, in this dynamic scenario, any sudden or important event can occur, and these event related information should be sent to the command center faster. So that's why our goal for this paper is to find out the content which are most priority and disseminate this prioritized content optimally. And we use reinforcement learning in this scenario. So our challenges is in this scenario we don't have any network infrastructure because we consider the network infrastructure is damaged or unavailable. That's why the nodes or soldiers, like their devices, they need to communicate with each other, and the information should transfer hop by hop, uh, and thus they create a delay tolerant network. That's why forwarding information um, is very difficult in this kind of scenario. So our goal is threefold. First of all, finding the important messages based on the trending topic. We mean trending topic, we mean that when an event is occurred, the topics related to the event becomes trending because many soldiers try to generate information about this event. So these event related messages should be forwarded to the command and control center faster. Our next goal is to satisfy soldiers' mission interest. That means that each soldier should collect information which are related to their interest or related to their mission goal. For this reason, they sometimes have to adjust their interest based on the contact with other nodes. So we'll explain this later. And our third goal is to control the congestion. Like if we forward information or receive information from a particular node too much, then this node may die. That means the device of that soldiers may consume too much battery and it will soon not work. So that is our third goal, to control the congestion. So let's first talk about our first goal, which is prioritize content by trending topic. So we know that in this kind of scenario, like sudden event can occur, like car bombing, for example. So nodes around this event, they will generate a lots of information about this event. So this information may include fire, smoke, injured person, these kind of topics. So these certain event-related topics or messages should be forwarded to the control center quickly, so that control center can adapt like appropriate actions quickly. So the problem is not all the nodes are interested in those topics. So they will not forward this information from one to another. But we need to make sure they forward, otherwise those important topics will not be is derived to the command center. So that's why we need to detail the trending topic and we need to forward messages associated with the trending topic. So how to find this trending topic? So the common concept of trending topic is they generate in a small area and they generate uh, in a short amount of time. So we can calculate the importance of topics using a modified version of term frequency inverse document frequency method. So here we describe how we calculate this. First, we discretize the time in several time windows. And for each time window, we track how many messages are generated for each topic. So then we consider few recent topics and we calculate the TF-IDF. But for calculating the TF value, we actually square the TF value in the TF-IDF method because many messages will be generated in a short time for an event, and that's why we want to increase the value of TF. But the problem is if several non-important messages with similar trending topics generated in a short time else are in the network, then this method will not work. That's why we need to consider the area also. That's why we calculate the standard deviation of the topics associated message location to find out how distributed they are being generated. So if we find some topics is hot by the TF-IDF value, we cannot be sure if it is actually hot because this topic can be generated in different area. That's why we calculate the standard deviation also. And if we find that the standard deviation is too much for some particular topics related messages, then we put the message as less important. So these are the equations of how we calculate modified TF-IDF. So the TF and IDF are pretty similar to the conventional method, and we also calculate the standard deviation for the messages for each topic. Then the TF-IDF is calculated as follows. We square the TF, then we take the log of IDF and we divide it by standard deviation. So that's how we calculate the importance of each topic. Now to calculate the importance of a message, we calculate the average of all the topics associated of this message. And that's how we calculate the priority of a message, which is the average of all the related topics, TF-IDF modified. Finally, we have to find out which are trending messages. So we consider a threshold. If the priority of a message is greater than the threshold, then we consider this message as trending. And we forward this message regardless of node's interest. Our next goal is to prioritize content by interest. So we know that different soldiers are associated with different mission goals, and for this reason they have different interest over the message. So if we consider messages are associated with different keywords, then a node is also associated with different interest. So a node might be interested of some particular message because its interest aligns with the keywords of the message. So thus we can find out the summation of weights of the interest of a node for some message, and this is called interest similarity, which can be calculated by this formula. So this interest similarity can be shared between the nodes when they are in communication range. However, we have to adjust the interest weight. Let's assume one example. So Alice wants to send message to Bob because they have similar interest, but they are not in communication range. That's why they have to send the information via another node, Chuck. But Chuck doesn't share their interest. In that case, Chuck will not receive message from Alice and Chuck will not deliver message to Bob, which will hamper the message delivery ratio. That's why we have to adjust Chuck's interest also, so that it will be willing to forward message from Alice to Bob. So we can adjust the interest based on nodes contact using Q-learning, which is a popular algorithm of reinforcement learning. So this is the equation for Q-learning. It says that the cumulative reward of a particular state and action can be updated by 1 minus learning rate into the cumulative reward plus learning rate multiply the reward current reward plus discount factor multiplied by the future maximum cumulative reward possible. So we fit this Q-learning in our scenario. So we define the state as each topic. So each topic is considered as the state. Action is when some node receives a message, all the associated topics will become the action. Finally, the reward. The reward is calculated by the amount of time a neighbor node with some specific topic interest remains connected. So it ensures that nodes whose connection time is more, their interests get more priority. That means if Chuck is connected to Alice more, then it will share some interest of Alice, so that it will receive information from Alice. So that is the concept. Now we have to define the parameters of Q-learning. So first parameter is the learning rate. So we keep it in our algorithm. We keep it fixed because most of the times the event message is not dependent on the interest. That's why if some event occurs, our Q-learning will get false idea that some node is interested in some other topics, which actually it is not. Now the discount factor gamma is calculated by the number of times a topic is collected from some receiver versus the number of times the topic is received in total. So that's how it gets mature for each topic. Then the reward is calculated by the connection time. So the more it is connected with some other nodes, the reward will be more. And finally, the interest weight can also be decayed based on the decay factor. It means that if some node with some particular interest is not connected to some other node with the same interest, the Q value for that topic will decrease. So that's how we adjust the interest of each node, each node. Then third goal is avoiding nodes congestion. So if some node is engaged with multiple, like too many message forwarding and receiving, then it will get congested because it will consume too much energy, and that's why its battery may die. So we have to avoid this kind of situation. So we first define the congestion ratio, which is the average amount of data received or transmitted by the total contact time. So we can calculate the exponential moving average of the congestion ratio. So our goal is to keep the EMA or exponential moving average of congestion ratio minimum for all the node or similar for all the node, so that one of a particular node will not die first. Again, we implement Q-learning for calculating the congestion. So we define the state as each node is considered a state. So message travels from one state to another state. That means one node to another node. Then action. Action means like which node I should select for forwarding the message. So I will always select the node which has less congestion or less amount of data transferring. Then reward. Reward is actually punishment, which is like inverse of congestion ratio. So if I forward messages to some node and it already has more congestion ratio, the reward will be less. Now we define the Q-learning parameters. So first one is alpha. Alpha is 1 by visit. That means the more time you visit some particular state and action, you will the learning rate will be less. So that it means that that state and action pair will get mature. Then the next parameter is discount factor, which is calculated as this. So it is related to the total reward received by the receiver. So that means that if a receiver node is involved with many message transfers so far, its learning about the other nodes are considered mature. Then the reward, which I already described, 1 by EMA of congestion ratio. So nodes thus learn about the better candidates among the receivers to forward information first. So by keeping these all goals in mind, we can define our routing as follows. So we can take this simple example. We see, let's say, a node already transferred a message to node 1. So this node 1 will be in pending state. It will receive the message. Then node N meets N2 and N3. So both are available. So we can see that the Q value of N2 is more. So it will select N2 for the next hop. Again, if we consider the trending threshold as 40, and if we calculate the modified TF IDF value of all the messages, we can find that M1, M2 is the trending message. So we have to send those message first. However, after sending those messages, we have these 3 messages remaining, and we can calculate the interest similarity. We can find that the most interest similarity can be get from M5. So M5 will be forwarded next, then M3, then M4. That's how the routing occurs. Then we calculated, we ran some experiments using one simulator for this following 2 datasets. One is STD's dataset, another one is EPFL mobility dataset. So these are the parameters. I will not describe them. These are just how much time we took for simulation, the node number, bandwidth, many the parameters for learning, etc. So the first graph states that how much network resource it took for these 2 datasets. So this is not related to our method. We just wanted to show that if the number of messages is high, if the bandwidth is high, then delivery ratio is high. Then if the buffer size is high, delivery ratio is high. So that is a few properties we wanted to describe. Then we wanted to show how the trending threshold affects in delivery ratio. We could say that if for different trending threshold, different delivery ratio can be achieved for different events. However, the delivery ratio for all messages are pretty same, which is not controlled by trending threshold. Then interest similarity, we can see that in our case the interest similarity is more. We compared it with another paper which also worked with same goal like interest similarity, and we found that without interest similarity we cannot satisfy nodes interest. Then we also saw that network bandwidth is less in our method because as nodes can satisfy their interest, they are involved in less number of message transfer and receiving. However, energy consumption is more in our method because it is always learning and this consumes energy. Then we can see the congestion effect during events. So this says that for different events, what is the delivery ratio if we consider the congestion or if we don't consider the congestion. We see that it is not much, but it still improves few percent of delivery ratio during events. So in this paper, we considered a battlefield or disaster scenario where many teams can work in different missions. Then we used Q-learning method, which is a reinforcement learning method for designing the effective content dissemination scheme. So our scheme uses continuous learning of content received, then the contact patterns of the nodes, and thus it can calculate the content prioritization and congestion avoidance. Currently, we are developing an in-rendered app based on this idea. That's it. Thank you.